Hello, my name is Awatif Garbua, and for my signature assignment, I am going to be talking about what is Coulomb's law. Coulomb's law gives us the method by which we can measure the electrostatic force between two charged objects. But what does this mean? We're going to go through it step by step, starting with an understanding of what is electrostatic force. Put simply, electric force is simply the transfer of electrons from one object to another. Electrons have a charge of 1.6 times 10 to the negative 19 coulombs, with coulombs being the measurement of charge. By comparison, protons have a charge of 1.6 times 10 to the positive 19 coulombs, with the value of the exponent denoting the charge, whether or not it is positive or negative. A positive charge will be repulsive, whereas a negative charge will be attractive. In other words, an electric field will emanate outwards from a positively charged object, whereas electric field will emanate inwards towards a negatively charged object. Much like magnets, a positively charged object and a negatively charged object will be attracted to each other, whereas two positively charged objects or two negatively charged objects will repulse each other. For a practical example of what is electrostatic force, I'd like you to consider the balloon and the hair. I'm sure you've done this as a kid. When you rub the balloon on your hair and then you lift it up, your hair sticks to the balloon and you get this fun levitating hair effect. The way that this works is that by rubbing the balloon on your hair, electrons are transferred from the surface of the balloon onto your hair follicles, giving the balloon a positive charge and the hair a negative charge. Because positive and negatively charged objects are attracted to each other, your hair sticks to the balloon, and when you lift it up, your hair levitates. So, let's talk about Coulomb's law. What it states, put simply, is that the electrostatic force between two charged objects will be proportional to their size or magnitude and inversely proportional to their distance. Let's break this down. Proportional to their size or magnitude refers to the actual magnitude of the charge itself, whether it is in the positive or the negative direction. If you make a charge stronger, then the electrostatic force between two charged objects will increase proportional to the increase in the magnitude of the force itself, or the charge itself, They are inversely proportional to their distance, which means if you take the two charged objects and you move them farther away from each other, the electrostatic force between them will go down proportional to that increase in distance. The formula for measuring Coulomb's law is that the electrostatic force between two objects, denoted by F and measured in newtons, will be equal to Coulomb's constant, denoted with K, multiplied by the magnitude of the first charge, denoted by Q1, multiplied by the magnitude of the second charge, denoted by Q2. You will then take the product of those two charges and you will divide them by the radius between them squared. How does this work? Well, let's first talk about what is Coulomb's constant, and by understanding Coulomb's constant, we will get an understanding of why this equation works. Coulomb's constant is equivalent to 8.99 times 10 to the 9th power, or, in other terms, 1 over 4 pi epsilon naught. Epsilon naught refers to how easily an electric field can form in a vacuum, or in perfect conditions where no other environmental factors exist. If you plug I over 4 pi epsilon naught into the formula for Coulomb's constant, which is, for a reminder, K multiplied by Q1, Q2 over R squared, then you will get this equation, which is Q1 times Q2 over 4 pi R squared epsilon naught. Do you notice anything about this equation? Because you should notice that 4 pi R squared is the surface area of a sphere. The surface area of a sphere refers to the electric field itself, because electric field is a sphere, and the charged object is going to be at the center of the electric field. So the farther away you get from the charged object, the weaker the electric field is going to be. I'm sure you've also noticed that the formula for Coulomb's constant is remarkably similar to the formula for measuring gravitational force, with the gravitational formula being that gravitational force is equal to the gravitational constant, which we will talk about in a second, multiplied by the mass of the first object times the mass of the second object, and then the product of those two masses is divided by the radius between them squared. There's a couple of differences that you should note here. First, in the gravitational formula, we are measuring mass, whereas in the formula for electrostatic force, we're measuring magnitude, right? The second is that the gravitational constant is 6.6743 times 10 to the negative 11th power. Now recall that the Coulomb's constant is 8.99 times 10 to the 9th power. This means that electrostatic force is 39 orders of magnitude larger than gravitational force. In other words, the electrostatic force between two charged objects is 39 orders of magnitude larger than the gravitational force between an object and the surface of the Earth. How crazy is that? It doesn't even sound like that should be correct. So I have included here a practice question. If you have a negative charge of negative 2 coulombs and a positive charge of 3 coulombs, separated by 80 meters of distance, what will the force be between the two charges? Now recall, the formula for Coulomb's constant is what? Electrostatic force is equal to Coulomb's constant multiplied by the magnitude of the first force times the magnitude of the second force divided by the radius between them squared. So we are going to plug our values into this equation to get F is equal to K times 3 times negative 2 divided by 80 squared. We're going to solve out the numerator and the denominator of our fraction, and that is going to give us negative 6 on the numerator and 6,400 on the denominator. So now we are going to divide negative 6 by 6,400 and multiply that to Coulomb's constant. If we perform the division, we are going to get a value of negative 0.0009375, which we are then going to multiply by 8.99 times 10 to the 9th power, Coulomb's constant. When we do that, what is the electrostatic force we're going to get? The electrostatic force between these two objects is going to be equal to negative 8,428,125 newtons. Did you get the correct answer? Finally, I'd like to talk about a real-world application for electrostatic force, and this is the Xerox printer, which was discovered in 1938 by Chester Carlson, who used Coulomb's law to create the first ever photocopying machine. I have attached here a diagram of how these machines work, and I have also included step-by-step how this process is going to work. Now, the first thing that we are going to do is take a thin layer of selenium. Selenium is used for this application because it is an insulator in the dark, which means that it does not conduct electrical energy, but in the light, it is a conductor, which means it is very good at conducting electrical energy, right? Keep that in mind. So because it is a conductor when exposed to light, we're going to take a negative image. And what a negative image means is that the actual image, or the thing that you are trying to photocopy, is going to be dark, and everything else is going to be light. And because selenium is a conductor when it's exposed to the light, everything except the image is going to be exposed and it's going to be uncharged. But because the selenium has a positive charge, recall that we gave it a positive charge, the image itself is now going to be positively charged. So what are we going to do with this positively charged image? Well, we are going to adhere some negatively charged powdered ink to it. This way the image will actually print. So now that we have our positively charged image and our negatively charged powdered ink on top of that positively charged image, and then the neutrally charged everything else, we're going to take a positively charged piece of paper and we're going to place it over the surface of our image, electrostatically printing this image, a process that you can see occurring right here. So now that we have the image electrostatically adhered to the piece of paper, we are going to adhere the ink to the paper via heat roller, which is pictured here. And this way, we have a photocopy of our image. So yeah, thank you for listening to my presentation on electrostatic force. And thank you for a great semester.